Lesson 26, linear motors. Lesson 26, in this last third of the class after the exam 2, it's a lot of applications of electrical engineering. And so with this, we're kind of moving into motors. And if I think motor, what does it do, right? Whenever I think of my car motor, I'm converting combustion into mechanical energy, right? Motors convert some form of energy, to what? To mechanical energy, right? We can also think that it creates movement, right? If I have a motor, I'm motorizing something, my car motor is turning combustion and it's outputting mechanical energy that's spinning something so that my car can move. So we're going to do the same thing with electrical motors. So electric motors are going to convert electrical energy into mechanical energy. So the way that our electrical energies, our electric motors will require a magnetic field interacting with current to create this mechanical energy or to create the movement. Okay, so let's talk about how that's working. Those are the two big things about motors. So let's just review about magnets. We've been talking about flux, right? Flux, where is it described here? I guess these lines of magnetic field, but these are lines of flux. There it is, the direction of the magnetic flux lines. So these are lines of flux, right? All the way going around from north to south. And the closer I am to my magnet, the stronger it is. So a stronger magnetic field is a stronger lines of flux. Now, we talked about this before, but if I have a current carrying wire, right? Here's a wire right here, and it's flowing through, sending current, I is going through, then it creates lines of flux that go around that wire. And now I call this the Gigam rule, and that's because there's two right-hand rules here. So at Texas A&M, if you're familiar, we say Gigam. When you say Gigam, you stick your hand up like this, right? Or thumbs up. But what we're doing is if my thumb is the current and the lines of the flux are my fingers. So here's the Gigam and there's the lines of flux. Okay, so there's a current carrying coil. Now, if I want to make this even stronger, I can create this wire, and instead of just sending it straight through, I send it in a loop. And when I send it in a loop, all of these lines of flux around each individual part of the wire all combine and they create even stronger lines of flux. And so this lines of flux, magnetic flux is going around like this. And if I stuck another magnetic field by having a coil on this side, we saw that we could induce a current on this other side. But now think about if I have two interacting magnetic fields, what's going to happen if I had current already going through one side and current going through the other? I like to think about my son's Brio trains, right? Whenever you stick the two trains next to each other, I can move one train without ever making them touch because I'm interacting their magnetic fields. So we're going to take this same idea now, and we're going to say that this is the Lorentz force. Lorentz force right here, and there is an equation for it, FD. So if I have my lines of flux and I say how dense are they, how strong, right? The stronger the magnetic field, then the stronger the density, right? The lines, if I think about going through an area, if I have an area and I have two lines of flux going through this area right here, that's less strong than if I had the same area and I had lots and lots of magnetic lines of flux going through it. This is a stronger, right? This one is stronger than this one. And so the magnetic field is stronger. And if I have a stronger magnetic field and I have a higher current, look at the parts of this, I have a current right here. There's my current. And then this is my magnetic flux density, right? The stronger field, stronger density. And so just like my son's Brio trains, if I had stronger magnets on them, I could push one further. Well, what happens here is if I place this bar, that can carry current going through it, and I make it where instead of just plugging it in, I just set it on top and so it forms an electrical connection, it will move. And that's what's going to happen here, is that we get a Lorentz force that is being created. This L is the length of the bar. So the L equals length of the bar. And that bar is carrying the current. And so right now, before we get into this linear motor and how we're making this happen, just observe that we have these right here. These lines of flux are going into the page. That's what the X means. And stop this video when you finish it, and we're going to watch an actual small example of a linear motor using a little battery on one side, using a battery on one side with a magnetic field that's existing, and we have a bar. Right here is the bar, and the bar is going to move in the direction of this F right here.